Let's do some magnetism demonstrations. It all started thousands of years ago when people had discovered metal and they found that some of the rocks had natural magnetic properties. They could pick up a piece of metal. This stuff is called lodestone, and you can see that it moves the needle of a compass. The compass was invented thousands of years ago in China when somebody took metal, like a needle, and rubbed it on a piece of lodestone. It became magnetic. That's just what I did here. I rubbed this on a magnet, and I put it in a cork. And now we're going to put this in a little tub of water. It naturally rotates and aligns with the Earth's magnetic field. Now, this is a repetition of a discovery from thousands of years ago. We can try it with some of these neodymium magnets and see what happens. Whoa, that's pretty quick. Obviously, this magnetic field of these magnets is much stronger than the needle. And that is, that's pointing north. I have a clamp on the door with some string hanging from it down to a brass holder. It's non-magnetic, holding up a bar magnet. Let's see what happens if I disturb it a little bit and let it go. Oh, it's realigning itself with the Earth's magnetic field. The real test will be if I switch the magnet around. Now I flip the magnet around, and the north wants to swivel around and come back to the same orientation. The north pole of a bar magnet points to the Earth's geographic north pole. What does that tell us about the magnetic pole at the geographic north pole? Opposites attract. Therefore, it's a south pole. The north pole of the Earth is actually a magnetic south pole. Well, what do we have here? I've got a bunch of iron filings, and they're sticking up into the air here. It's all coming from this big horseshoe magnet I have. I've clamped the magnet down, and now I'm sliding the paper around on it. And it gives you an idea of what the field lines look like from the magnet. They come out one side of the magnet and go through three-dimensional space back into the other side. The field lines continue around through the magnet and then come back out over here. Magnetic field lines do not have a beginning or an end. They keep forming loops. So just where do these magnetic fields come from? I have my power pack hooked up to some wires. The wire is draped over a compass. We can see the needle on the compass somewhat parallel to the red wire. I'm going to turn on the current, and it deflects the needle. I'm going to put the compass on top of the wire, turn on the current, and it deflects the needle the other direction. The red wire is connected to the positive terminal, and the positive charges are going to flow across like this. The right-hand rule for the creation of the magnetic field tells us put the thumb in the direction of positive motion, and the fingers will curl around, forming a loop in the direction of the field lines generated by the motion of this charge. I'm turning the current on and off. Magnetic fields are generated by charged particles in motion. Putting the compass on top of the wire makes the north pole of the magnet align in the opposite direction. My fingers are going to curl around, and the field will be going in this direction on top and that direction on the bottom. So it looks like this. We can concentrate the magnetic field produced by the charges moving in the wire by wrapping them in tight circles. We're going to put it around a soft metal nail which carries the magnetic field lines better than just air. With the current off, the nail is not picking up the paper clip. But if I turn the current on, we have an electromagnet. I turn the current back off, and it's not picking it up. Now this electromagnet has to have a north pole and a south pole. How do we know which is which? Well, we can test it with the compass. I'm going to turn on the current, and the north pole is pointing to this end, which means this must be a magnetic south pole. Look closely at the way the charges are going to flow around this wire. Could you use the right-hand rule to figure out why it works this way? Putting the compass on the other end, let's see what happens. That's the south pole of the needle of the compass. It must be attracted to the nail, which must be a north pole then. Here's another interesting demonstration. This is the oscilloscope, and that green dot at the center of the screen is light coming from the screen because a beam of electrons is accelerated toward the screen from the back of the oscilloscope in a vacuum tube. That beam of electrons smashes into the phosphor coatings on the back of the glass, and it gives off light. Now that's an electron beam. I have magnets here taped together. Let's see what it looks like when I put the magnets near the oscilloscope. Okay, I bring the magnet down, and the beam gets deflected to the side. I'm going to rotate the magnet, and now the beam gets deflected in the other direction. If I put the magnet on the side, the beam is getting deflected down. Rotate it this way, and the beam gets deflected up. Well, this tells us something about charged particles moving through magnetic fields. Can you use the second right-hand rule to tell us why that beam moves the way it does? Here I have the magnet near the compass. The south pole of the compass is pointing to this side of the magnet. Well, that means this must be the north pole. Let's come over to the oscilloscope and see what happens. If I put the north pole of the magnet near the screen, the beam is getting deflected down. If I put the north pole on top, the beam gets deflected to the left. Don't forget that the beam is negative, coming towards us.